Last time we looked at scheduling for CPUs, and we made a lot of assumptions about the different processes that will arrive and like what the properties of those processes will be. So today let's actually like remove some of those assumptions and then talk a little bit more about the actual complexities of scheduling. So one of the first things that we said was like your process is going to just be crunching numbers. It's going to be using just the CPU. Now, in actuality, most of your processes will be showing something on your screen, will be writing and reading from files, maybe sending something off on the network or printing something on your printer. So the key point is that processes do engage in what we call input and output. So they will be sending stuff to the screen or the printer or whatever. So broadly we call this I/O, how a process communicates with the external world. And one of the important features of I/O is that it is very, very slow when compared to just doing computation. So to give you sort of like a quick comparison point, when you're reading a register, that takes the register that we just saw, like for example, EAX, which contains the return value of functions in GCC. So reading that register takes like one cycle on your processor. So that will be roughly like anywhere between half a nanosecond to like 1 or 2 nanoseconds on older machines. So it's around a nanosecond, let's say. Whereas and 1 nanosecond is what's a good way to put it? It's one part of like 10 power 9. It's not a great way to put it. 1 nanosecond is like 1 to the power 10 minus 9 of a second. So to put it another way, there's 1 billion nanoseconds in a second. That's sort of like an easier way to put it. So to read a register, it just takes 1 nanoseconds. Whereas let's say you want to read from a file. Let's say you're reading like just like 1 byte from a file, and even on sort of like modern storage devices such as solid-state drives, that is going to take you somewhere between 50 to like 200 microseconds. And a microsecond, and there are a million microseconds in a second. So that is roughly, if you think about it, that's about like more than 1,000 times slower than just reading a register. So whenever you're doing I/O, that's usually like a big part of time in which like the process cannot do any computation. So when you're scheduling these things, this is something you have to take into consideration. So if let's look at like the different states a process can be, and sort of we'll work that in. So initially, so if you look at the iPad, initially there will be a process which is just created. This is init. Now, this is a state where the process is just like, you're setting up all the stuff you need for a process, all the variables, the kernel state, the user space state, and so on. So the stuff that we looked at when you're creating a process, you'd have to set up, for example, the stack, the heap, the instruction pointer, the stack pointer, and all of that stuff. So all of that happens in init. Right, and after that, once all of this is done, the next state is called runnable. So this is a state for each process where it is eligible to be run on the processor. There's nothing that it is waiting for. All its variables, everything is like set. So typically, once you've done init, it goes into the runnable state. From the runnable state, if your scheduler actually picks up your process and runs it on the CPU, it goes to the running state. So there can be lots of runnable processes, and of them you're actually you're picking one and you're running it on the processor. That's the running state. Now let's say it wants to read from a file or write to a file. At this point, what happens is it is usually in a state where it is waiting on I/O. Sorry. So this is the reason this state exists is because it can take usually a long time. Like because doing I/O is about 1,000 times slower than reading from register. You can actually you can schedule a number of other processes while this particular process is just like waiting for something to be shown on screen. Right? So because of that, we have the waiting on I/O state, and this has many names. For example, blocked on I/O is a different way to put it. But the process is waiting on I/O, and sometimes the I/O finishes, and now the process is unblocked. So when the process is unblocked, it goes again into the runnable state. So it's now eligible to be run again. And from that state, it once again goes to running. And once the process is finished running, it usually is it's done. And sometimes what happens is that it's in what we call a zombie state. Right? The zombie state is when it's finished running, but there's still some event in the system that has to happen for it to be fully deleted and flushed out of the system. And we'll learn about some of these events sort of later in the course, but that's another state that the process can get to. Right. So these are all. If you look at sort of like the scheduler of a modern operating system, these are all states that sort of like the operating system or the kernel has to handle. Right. Another aspect that we didn't talk about last time when we were looking at scheduling is that we talked about as if like there's only one processor at all points of time. And this is not true. Like modern laptops and servers definitely have more than one processor. So let's call it like CPU 1, CPU 2, and CPU 3, right? And then let's say you have process A, process B, and then process C, right? Now one other metric that people sort of like look at when doing scheduling is load balancing, right? So you have 3 processes that need to be scheduled, and you have 3 CPUs that are waiting for something to run. And so a fair way to do this would be just to say process A runs on CPU 1, process B on CPU 2, process C on CPU 3, right? So this is a fair way to distribute the load, right? We call this a balanced system. Another way to do this would be to say we're going to load, we're going to execute both process A and process B on CPU 1. You're going to time share, and you're just going to let CPU 2 be idle, and then you're going to do process C on CPU 3, right? This is sort of like an unbalanced system, right? And there are many sort of like valid reasons in which you wouldn't actually utilize all your CPUs all the time. So for example, let's say there is a special very high priority process. Let's call it process Z, right? Whenever process Z arrives on the scene, we want to schedule it immediately. And because of that, let's say we keep a CPU idle, and whenever process Z comes, it is scheduled on CPU 2 immediately. Now, this is not a scheme that people actually use, but you could imagine doing some variant of this if you want to schedule process C whenever it arrives on the scene with like 0 latency for scheduling, right? So that's another metric that people have to consider when doing scheduling policies, like how do you ensure fairness and load balancing across different CPU, right? So one other thing I sort of like didn't touch on is the concept of like a parent process and a child process. This will make more sense as we sort of like do more of the course, but in most operating systems today, you can actually have this parent-child relationship. So this is the parent, and then you can create a child, and that would be this. Right, and then your parent process actually creates the child process. And of course, a single parent can have many children, and so on. The reason they're doing this is because initially, if you look at your operating system, there is usually like only one process in Linux at least. It's called the init process. This process is the parent of like, or at least ancestor of all the processes that you're going to run on your Linux operating system. At the start, there was only init, there was nothing else, and all the different processes in your system, like your shell, for example, everything is a child of init. Let's say you're running a C program, right? And if you're running a shell, and then like if you type a command, that command is usually a child of shell itself. So you can have this sort of like hierarchy where init is the ancestor of everything, and it spawns things like the shell, which then spawns other commands. Now, one of the interesting things about the parent-child relationship is that the child inherits a lot of stuff from the parent. So, for example, if the parent was doing some work in memory, now when you create a child, the child also has a copy of that. And we'll get into this more as we do memory management. But the parent-child relationship sort of like special in most operating systems. And the state that we talked about, zombie, right? That's a state where, let's say, your child has existed. Your parent can wait for all child processes to finish execution before it sort of like continues. And when you're waiting for such an event to occur, then that's when you can get into the zombie state, where you're finished executing, but you're waiting for somebody to clean you up, right? And we'll get into this more, and like, one of the projects that you'll do in this course will sort of like deeply involve like parent and child processes and shell. So you'll get like a strong feel for this as the course goes on. So with that, like I hope you understood more about like how the complexities of scheduling policies. So next we'll be looking at how scheduling works in our educational operating system XV6, and we'll also take a look at like how scheduling works in the Linux kernel.